This is a P3 replay for the reactions of heterocycles lesson, and by this point in the semester you're probably used to using things like SHMO and thinking about the reactivity of heterocycles. But these problems sort of bring it all together and ask us to predict the product of a reaction given to us. In fact, in these P3s, you're actually given that we're looking at the HOMO of the pi system, which means that the heterocyclic compound is serving as a nucleophile here. The problem asks us to input the molecule into the SHMO calculator and examine its HOMO in there. So I'll go through that very quickly, just a short tutorial for SHMO. You'll automatically be in the add mode when you load SHMO, and you can just click and drag to create rings or linear pi systems. I like to lay down all of the atoms involved first. Remember only to draw sp2 hybridized atoms. In this case, every single atom in the heterocycle is sp2. Minimize and then change. You'll use change to adjust carbons to heteroatoms. And when you lay down heteroatoms, make sure to distinguish them based on their connectivity. So in this case, we're interested in placing an O2 rather than an O1 because the oxygen is connected to two other atoms. I like to minimize one more time for my own sanity and then click Show Orbitals to reveal the molecular orbitals of the compound. The HOMO is the highest orbital that contains electrons, the highest energy orbital that contains electrons. And we can see from the HOMO that it's the atom next to oxygen in the five-membered ring that has the largest coefficient. This is the most nucleophilic atom in the compound shown here. So I'm going to copy this structure, paste it, and immediately do something with this atom, right? I'm not sure what's happening here yet, but I'm just going to add a methyl group there as a mental reminder that I'm going to use that carbon initially. Now, it's also important to understand the nature of the other reagent, right? So the other reagent is acetyl chloride. That's this compound here, and it's acting as an electrophile. Hopefully you're somewhat familiar with the acid chloride functional group. This is an electrophilic functional group that's perfect for acyl substitution reactions, where we're going to essentially substitute the chloride, as we would substitute a halogen, say in an SN2 reaction, by addition to the carbonyl pi bond followed by elimination. So essentially what's going to happen is we're going to replace the chlorine with the entire heterocycle. To depict this, I'm just going to erase the chlorine and then form a bond between that carbon that I sort of earmarked earlier and the carbonyl carbon here. I don't like these bond angles, so I'm going to clean it in 2D, and here we have a very nice structure to submit. You can also use resonance structures to see why this is the most nucleophilic carbon. If I erase this and I imagine using the double bond and leaving behind a positive charge, what you can see is that this positive charge is highly delocalized throughout the pi system, right? It's delocalized here, potentially here, here, and here, as well as onto the oxygen. So all of these carbons into which it's delocalized stabilizes that positive charge and explains why this position is the most nucleophilic.